280 million years after the Big Bang, a galaxy existed, not a faint smear of primordial gas, not a theoretical possibility buried in a simulation. A galaxy, compact, chemically enriched, already clearing the hydrogen fog around it, observed, measured, and spectroscopically confirmed by the James Webb Space Telescope in the spring of 2025. Its name is MOM-Z14. Its redshift is 14.44. And when Rohan Naidu at the MIT Kavli Institute published the data, he did not use the language of routine discovery. He wrote that what they found looks nothing like what they predicted. That sentence deserves a moment, because Naidu is not a commentator, he is not a journalist, he is the lead scientist on the observation. And what he is telling us is that the most distant confirmed object in the history of human observation does not match the models we built to explain the universe. This is not a story about a telescope finding something far away. Every generation of telescopes finds something farther than the last. This is a story about what was found when we got there, and why it has forced the scientific community to confront a possibility that 3 years ago would have seemed premature to even suggest, that the early universe was a radically different place than we assumed, operating under physical processes we do not yet fully understand. Over the course of this video, you're going to learn exactly what the James Webb Space Telescope has discovered at the farthest observable edges of the cosmos. But you're going to see the complete timeline of distance records that have fallen since July 2022, each one arriving faster and more disorienting than the last. You're going to understand why galaxies containing hundreds of millions of solar masses of stars exist at a time when our best models say they should not. You're going to meet the supermassive black holes that appear to have grown faster than any known physical mechanism can explain. And you're going to hear, in their own words, what the scientists leading this work believe it means, and where they disagree. By the end, you will understand why a growing number of astrophysicists now believe that galaxy formation in the first few 100 million years was not a slow, tentative process, but an explosive, an efficient engine of creation that we never predicted and are only now beginning to see. Let us begin with the instrument that made all of this possible. The James Webb Space Telescope launched on December 25, 2021, aboard an Ariane 5 rocket from Kourou, French Guiana. 1 month later, it arrived at its permanent station, a halo orbit around the Sun-Earth L2 Lagrange point, 1.5 million kilometers from Earth. Its first science images were released on July 11th and 12th, 2022, and from that moment forward, the records began to fall. But to understand why Webb sees what no other instrument can, you need to understand what it actually is. The primary mirror is 6.5 meters across, 18 gold-plated beryllium hexagonal segments working as a single surface, and that gives it a collecting area of 25.4 square meters, roughly 6 times that of the Hubble Space Telescope. It observes in wavelengths from 0.6 to 28.5 micrometers, spanning the near-infrared through the mid-infrared. And that wavelength range is not arbitrary. It is the entire reason this telescope exists. Light from the earliest galaxies in the universe has been traveling for over 13 billion years. During that journey, the expansion of the cosmos has stretched those wavelengths, a process called redshift, pushing what was once ultraviolet and visible light deep into the infrared. Hubble could not see it. Ground-based telescopes, fighting through Earth's atmosphere, could barely glimpse it. Webb was designed from the ground up to capture exactly this light. To look back not just far, but to the very beginning, 4 instruments divide the work. NIRCam, the primary imager, covers 0.6 to 5 micrometers. Its principal investigator is Marcia Rika at the University of Arizona. NIRSpec, built by Airbus for the European Space Agency, is a multi-object spectrograph with 250,000 configurable microshutters, capable of observing approximately 200 objects simultaneously. This is the instrument that confirms distances. Without NIRSpec, every galaxy candidate remains exactly that, a candidate. MIRI, the only mid-infrared instrument, operates at wavelengths up to 28.8 micrometers and must be cooled to 6 to 7 Kelvin by a dedicated cryocooler. And FGS/NIRSS provided by the Canadian Space Agency It handles fine guidance and slitless spectroscopy. The telescope cost approximately $10 billion across all partners. NASA's share was roughly $9.7 billion. The European Space Agency contributed around €700 million, including the Ariane 5 launch vehicle. The Canadian Space Agency contributed approximately $200 million Canadian dollars. It was, by any measure, the most expensive and complex scientific instrument ever placed in space, and it nearly did not survive. The Ariane 5 launch was so precise that Webb conserved far more station-keeping fuel than engineers had planned for. The original design lifetime was 5 to 10 years. Current estimates now place the operational lifetime at roughly 20 years, potentially through 2041. As of April 2026, all 4 instruments remain fully operational with no mission-limiting issues. The telescope is currently executing Cycle 4 observations, and Cycle 5 selections were announced in March 2026. 254 programs chosen from a record 2,855 proposals submitted by over 7,000 investigators across 849 institutions worldwide. Cycle 5 was 9 times oversubscribed. The demand to use this telescope has never been higher. Now, with that instrument in mind, consider what it was pointed at and what it found. Before Webb, the most distant confirmed galaxy in the universe was GN-Z11, observed by the Hubble Space Telescope in the Candle survey. Its spectroscopic redshift was 10.957, placing it approximately 400 million years after the Big Bang. That record stood from 2016 until Webb's first year of operations. And then the floodgates opened. In December 2022, a team led by Emma Curtis Lake at the University of Hertfordshire announced the spectroscopic confirmation of JADES-GS-Z13-0 at a redshift of 13.2. 320 million years after the Big Bang, it was compact, roughly 50 parsecs across, with a stellar mass of about 63 million solar masses. It was the first galaxy confirmed by Webb to break GN-Z11's record, and it would not hold the title for long. In May 2024, the JADES survey team, led by Stefano Carniani at the Scuola Normale Superiore in Pisa, alongside Brant Robertson at UC Santa Cruz and a large international collaboration, announced JADES GSZ 14.0 at redshift 14.32, approximately 290 million years after the Big Bang. This galaxy was over 1,600 light-years across, with an estimated stellar mass of 500 million solar masses. A follow-up observation in March 2025, using the Atacama Large Millimeter Array, detected oxygen emission from this galaxy at a refined redshift of 14.1793, the most distant detection of oxygen ever recorded. Oxygen, which can only be produced inside stars and dispersed by supernovae, had already been manufactured and distributed across this galaxy less than 300 million years into cosmic history. That single measurement challenged assumptions about the pace of chemical enrichment in the early universe, and then in January 2026 came MOM-Z14, their redshift 14.44, 280 million years after the Big Bang. Led by Rohan Naidu at M1T, observed with NIRSpec on April 16, 2025, the preprint appeared on Arxiv in May 2025 and was published in the Open Journal of Astrophysics in January 2026, with joint NASA and ESA press releases on January 28. This galaxy is approximately 50 times smaller than the Milky Way, comparable in mass to the Small Magellanic Cloud, yet it is brighter, more compact, and more chemically enriched than any model predicted for that epoch. Elevated nitrogen-to-carbon ratios indicate that massive stars had already formed, lived their full lives, and died, seeding the surrounding gas with heavy elements. And the galaxy had cleared the primordial hydrogen fog around it. At 280 million years old, the universe had barely reached 2% of its current age, and already stars were being born, were dying, and were reshaping their environment. Jacob Shen, a co-author on the MOM-Z14 paper from MIT, stated plainly that there is a growing chasm between theory and observation related to the early universe. To place these distances in human terms, Though human terms are arguably inadequate, the light from MUMS E14 travelled for over 13.5 billion years to reach Webb's detectors. But because the universe has been expanding throughout that journey, MOM-Z14's current physical distance from us is roughly 34 billion light-years. We are observing it as it appeared when the entire observable universe was less than 1/50th of its present size. And there is a critical lesson embedded in this timeline that deserves attention, because not every claim of a record-breaking galaxy survived scrutiny. In August 2022, a galaxy designated CEERS-93316 was assigned a photometric redshift of 16.7 by Callum Donnan at the University of Edinburgh. Had that number been correct, it would have been the most distant galaxy ever detected, by a wide margin. But photometric redshifts are estimates, derived from a galaxy's colours rather than its spectrum. When Pablo Arabal-Haro at NOAA Lab obtained spectroscopic data, the true redshift turned out to be 4.9. Not the edge of the observable universe, a dusty foreground galaxy, orders of magnitude closer. A systematic study found photometric redshifts were biased high across the board. Stephen Finkelstein at UT Austin warned that claims of record-breaking photometric redshifts should be treated with caution. Today, only spectroscopically confirmed redshifts are considered definitive for distance records. Every galaxy named in this video has been spectroscopically confirmed. What you have heard so far is remarkable enough. The farthest objects ever observed by any instrument in human history, each one arriving with properties that challenge predictions. But the distance records are only the beginning, because it is not how far these galaxies are that has unsettled the scientific community. It is what these galaxies contain. In 2023, a paper appeared in Nature that changed the trajectory of an entire field. Ivo Labe at Swinburne University in Australia, along with an international team of collaborators, reported the detection of 6 candidate massive galaxies at redshifts between 7.4 and 9.1. That places them between 500 and 700 million years after the Big Bang. Their estimated stellar masses exceeded 10 billion solar masses. One of them rivaled the Milky Way. Let that register. The Milky Way is 13.6 billion years old. It has had the entire history of the universe to accumulate its mass. And here was a galaxy, observed less than 700 million years after the Big Bang, that had already assembled a comparable amount of stellar material. The standard Lambda-CDM cosmological model, the framework that has successfully described the large-scale structure and evolution of the universe for decades, predicted virtually no galaxies this massive at those times. Not rare ones. Not unusual ones. Essentially none. Mike Boylan-Colchin at the University of Texas at Austin published a key analysis in Nature Astronomy in 2023 titled Stress Testing Lambda-CDM with High Redshift Galaxy Candidates. His calculations showed that for these galaxies to exist at the observed redshifts, they would need to have converted nearly 100% of all available baryonic gas into stars. Every atom of hydrogen and helium within their gravitational reach would need to have been processed into stellar material with perfect efficiency. In the real universe, typical star formation efficiency is 10 to 20%. The rest is blown away by radiation pressure, supernovae, and galactic winds. 100% conversion is not just unlikely. It is, under known physics, essentially impossible. And Labe's galaxies were not an isolated anomaly. They were the first wave. Subsequent discoveries amplified the tension. A University of Geneva-led team published findings in Nature in November 2024 describing what they called red monsters, 3 ultra-massive galaxies approaching Milky Way-mass within the first billion years of cosmic history. Their star formation efficiency was measured at nearly twice that of galaxies in later epochs, not marginally higher. Double. These galaxies were building stars at a rate that existing models could not reproduce without fundamental changes to the underlying physics of gas cooling, feedback, and collapse. Then came Ruby's EGS-QG1, a galaxy with a stellar mass of 100 billion solar masses, and it had already stopped forming stars. It was quiescent, dead, sitting silently at a look-back time of just 1.2 billion years after the Big Bang, Published in Nature Astronomy, the authors described it as posing a major challenge to all current theoretical models, because the problem is not merely that this galaxy existed. The problem is that it had already lived its entire active life and shut down star formation before the universe had completed 10% of its current age. Whatever process built it operated on a timescale that our models simply do not allow. The structural maturity of these early galaxies added another layer of disorientation. In December 2025, Rashi Jain at the National Centre for Radioastrophysics in India published a discovery in astronomy and astrophysics that stopped many researchers mid-sentence. A galaxy they named Alaknanda, a grand-designed spiral galaxy, with fully formed spiral arms and Milky Way-like structure, observed at just 1.5 billion years after the Big Bang. Spiral structure requires time. It requires a rotating disk to settle, density waves to propagate, and gravitational interactions to stabilize. The conventional expectation was that such galaxies should not appear until several billion years into cosmic history. Alaknanda appeared billions of years ahead of schedule. It was not alone. The Big Wheel galaxy, published in Nature Astronomy in 2025, is a rotating spiral disk observed approximately 2 billion years after the Big Bang, and it is 3 times larger than cosmological simulations predict is possible at that epoch. Leonardo Ferreira at the University of Nottingham, surveying galaxies across redshifts from 1.5 to 8, but found far more disk galaxies than anyone expected. The title of his paper captures the mood of the field in 4 words: panic at the disks. Now, an important counterpoint. Not every observation points in the same direction. A 2025 study from Cambridge, led by Dan Hive and published in the monthly notices of the Royal Astronomical Society, analysed over 250 galaxies at redshifts between 4 and 6. Their conclusion: the majority of early galaxies were turbulent, clumpy systems that had not yet settled into organised structures. The mature spirals and massive quiescent galaxies may be statistical outliers, the exceptional cases, not the norm. This does not erase the problem. Even one galaxy like RUBIES-EGS-QG-1 demands an explanation, but it does suggest that the early universe was not uniformly precocious, that it was messy, chaotic, and occasionally, inexplicably, capable of producing something extraordinary, far ahead of when it should have. And this is the crux of what makes the James Webb Space Telescope's findings so significant. It is not that one galaxy breaks the models, it is the accumulation. Record after record, object after object, each one sitting slightly outside the boundary of what was thought possible. Individually, each could be explained. Collectively, they form a pattern that demands a response. But the galaxies are only half the story. Because inside many of these early galaxies, Webb found something else, something that, in many ways, is even harder to explain. If you have followed this video to this point, you understand that galaxies in the early universe are more massive and more structured than predicted. But what comes next is arguably more unsettling, because the James Webb Space Telescope has also uncovered a population of supermassive black holes in the first billion years of cosmic history that are far too massive relative to their host galaxies. In the local universe, in galaxies we can study in detail, the ratio of a black hole's mass to its host galaxy's stellar mass follows a well-established relationship. Supermassive black holes typically represent a small fraction of a percent of their galaxy's total stellar mass. What Webb is finding in the early universe is black holes with mass ratios of 30% or higher, 1 to 2 orders of magnitude above the local value. These black holes are not just large, they are, relative to their surroundings, grotesquely oversized. This creates what astrophysicists call the seeding problem. Supermassive black holes in the present universe are understood to have grown over billions of years through accretion and mergers. But in the early universe, there has not been enough time. A black hole that forms from a collapsing massive star begins at perhaps 10 to 100 solar masses. To reach millions or billions of solar masses in a few 100 million years, it would need to accrete matter at or above the theoretical maximum, the Eddington limit, continuously, without interruption, for the entire available time. That is not how accretion works. It is messy, episodic, and self-regulating. The radiation produced by infalling matter pushes back against further infall. The system throttles itself. And yet, there they are. Among the strangest discoveries are the objects known as little red dots. Of 341 compact red-tinted objects identified across redshifts from approximately 2 to 11, about 80% show broad emission lines characteristic of active galactic nuclei, the signature of matter spiraling into a supermassive black hole. They are roughly 10 times more numerous than previously known active galactic nuclei at redshifts between 5 and 7. Their nature remains one of the most actively debated questions in observational astrophysics. Some appear to be genuine active galactic nuclei. Some may be ultra-dense star-forming galaxies. Some may represent an entirely new category of object. A 2025 Nature paper by Roberto Maialino at Cambridge found that electron scattering effects in these objects could mean that initial black hole mass estimates were as much as 100 times too high. If Maialino is correct, much of the apparent overmassive problem dissolves. If he is not, the seeding problem remains acute. Specific discoveries sharpen the picture further. In December 2025, a galaxy observed at 800 million years after the Big Bang, informally named Virgil, was published in the Astrophysical Journal. In visible wavelengths, it looks ordinary, unremarkable. But in the mid-infrared, MIRI revealed a massive accreting black hole hidden behind a veil of dust. George Riquet at the University of Arizona, the principal investigator of MIRI, stated that Webb has shown that our ideas about how supermassive black holes formed were pretty much completely wrong. He added that it looks like the black holes actually get ahead of the galaxies, forming first or at least growing faster than the stars around them. In November 2025, KNX LRDZ 8.6 was published in Nature Communications, an actively growing supermassive black hole confirmed at just 570 million years after the Big Bang. In July 2025, Matsuoka and colleagues revealed in the Astrophysical Journal that luminous quasars are at least twice as common in the early universe as previously estimated, with many hidden behind dust, harboring black holes of billions of solar masses. There are currently 3 leading theories for how these black holes could have formed so quickly. The first is the light seed model. Black holes begin as stellar remnants of 10 to 100 solar masses and grow through sustained super-Eddington accretion, feeding faster than the theoretical limit by channeling matter through dense, optically thick flows. Simulations published in Nature Astronomy in January 2026 by Mehta and colleagues at Maynooth University suggest this is physically possible under the chaotic conditions of the early universe, though it requires very specific environmental conditions. The second is the heavy seed model. Black holes form not from dying stars, but from the direct gravitational collapse of massive primordial gas clouds, beginning at 10,000 to 100,000 solar masses. This gives them a significant head start. The Infinity Galaxy, 2 colliding disk galaxies with a 1 million solar mass black hole nestled between their nuclei, is considered a key candidate for this formation pathway. The third possibility is primordial black holes, formed in the first moments after the Big Bang itself, before stars existed at all. This remains the most speculative of the 3. None of these theories has been confirmed, none has been ruled out. The debate between them is one of the most consequential in modern astrophysics, because the answer will determine not only how black holes form, but how galaxies themselves are assembled around them, or perhaps because of them. What you have encountered so far in this video, galaxies too massive, too early, and black holes too large, too fast, represents a challenge to a specific layer of our cosmological understanding. Not the deepest layer, not yet. But there is another set of discoveries from Webb that reaches further back, into the first light that ever shone in this universe. And those findings carry implications that may outlast everything else. The cosmic dawn is not a metaphor. It is a technical term for a specific epoch, the period when the first stars and galaxies ignited and began flooding the universe with ultraviolet radiation, ionizing the neutral hydrogen that had filled all of space since the cosmic microwave background was released roughly 380,000 years after the Big Bang. Before this epoch, the universe was dark, not merely unobserved, physically dark. No stars had formed, No light sources existed beyond the fading afterglow of the Big Bang itself. The hydrogen gas that permeated all of space was electrically neutral, opaque to most radiation. The universe was, in the most literal sense, in a dark age. The process by which light returned, reionization, was one of the most important transformations in cosmic history, and for decades, one of its central questions remained unanswered. What produced the radiation that reionized the universe? The obvious candidates were the massive, luminous galaxies visible at high redshifts, but there were never enough of them. Their numbers and luminosities, even under the most generous assumptions, could not account for the total photon budget required to ionize all the hydrogen in the observable universe by the time reionization was complete, roughly 1 billion years after the Big Bang. In February 2024, Hakim Atek at the Sorbonne and the Institut d'Astrophysique de Paris published a landmark paper in Nature that provided the answer. Using Webb's extraordinary sensitivity to detect galaxies far too faint for any previous telescope, Atek's team demonstrated that dwarf galaxies, small, low-mass galaxies outnumbering their massive counterparts by approximately 100 to 1, were the primary drivers of reionization. These galaxies emitted 4 times more ionizing radiation than previous estimates had assumed. Not 4% more, 4 times. The photon budget balanced. The mystery, decades old, was effectively resolved. Atek described the result as revealing the global transformation of the entire universe, driven not by the brightest and most massive objects, but by the smallest and most numerous. This finding carries a broader implication that is easy to overlook. It means the early universe was not shaped primarily by the rare and spectacular. It was shaped by the common and the faint. The galaxies that rewrote the chemistry of all space were individually unremarkable. Collectively, they changed everything. Webb is the first telescope capable of seeing them, and without it, this piece of the puzzle would have remained missing. The cosmic dawn has also yielded the most distant supernova ever observed. In March 2025, the SVOM satellite detected a gamma-ray burst designated GRB2-50314A. Approximately 110 days later, Webb confirmed the source, a supernova at a redshift of approximately 7.3, corresponding to 730 million years after the Big Bang. The results were published in December 2025 in Astronomy and Astrophysics by Andrew Levan at Radboud University and the University of Warwick. What made this discovery significant was not merely the distance, it was what the supernova looked like. And scientists had expected that supernovae in the early universe, produced by stars with much lower metallicity than modern stars, would behave differently. Different compositions, different explosion mechanisms, different light curves. Instead, this supernova was surprisingly similar to those observed in the present-day universe. Stars at the edge of the cosmic dawn, it appears, die in much the same way stars die now. Whatever differences exist in how they form, the physics of their destruction has remained remarkably consistent across 13 billion years. The search for the very first generation of stars, the theorized population 3 stars, formed from pure hydrogen and helium with 0 heavy elements, remains one of the most important open quests in all of astrophysics. These stars have never been definitively observed. That their existence is predicted by every model of the early universe, and their fingerprints, unusual chemical ratios, extreme luminosities, characteristic spectral signatures, are actively being hunted in Webb data across multiple survey programs. As of April 2026, several promising candidates have been identified, but none has been confirmed beyond dispute. When that confirmation comes, and most scientists believe it is a matter of when, not if, it will represent the detection of the first objects that ever produced light in this universe. And the pace of discovery is not slowing. In the last 6 months alone, 5 findings from Webb have reshaped specific areas of our understanding, each one adding a new dimension to the picture of an early universe far more complex and active than anyone anticipated. In January 2026, a paper published in Nature described JADES ID1, the most distant protocluster ever detected with X-ray emission, observed at a distance of 12.7 billion light-years. Led by Akos Bogdan at the Harvard Smithsonian Center for Astrophysics and Christopher Consolis at the University of Manchester, the discovery combined data from the Chandra X-ray Observatory and the James Webb Space Telescope. The protocluster contains at least 66 member galaxies with a combined mass of approximately 20 trillion solar masses. Protoclusters are the ancestors of the massive galaxy clusters we observe today, the largest gravitationally bound structures in the universe. Finding one this massive, this early, with X-ray emission indicating extreme energetic processes already underway, that pushes the timeline of large-scale structure formation earlier than expected. Also in January 2026, a discovery published in Nature Astronomy revealed what has been informally called JWST's quintet, 5 galaxies in the process of merging at a redshift of 6.71, approximately 800 million years after the Big Bang. Led by Wada Hu and Casey Papovich at Texas A&M University, the system is forming stars at a combined rate of roughly 250 solar masses per year, surrounded by an extensive halo of oxygen-enriched gas. The significance is twofold. First, galaxy mergers at this epoch were expected to be rare. Finding a 5-way merger suggests the early universe was far more dynamically violent than simulations predict. Second, the oxygen-rich gas halo indicates that chemical enrichment had already extended well beyond the galaxies themselves, polluting the intergalactic medium with heavy elements manufactured inside stars. In that same month, the Cosmos Web Survey team published the most detailed wide-area dark matter distribution map ever produced in Nature Astronomy. By measuring the shapes of approximately 250,000 galaxies and analyzing how their light is subtly distorted by the gravitational influence of intervening dark matter, the team achieved an angular resolution of 1.00 plus or minus 0.01 arc-minutes, double the resolution Hubble could achieve. Researchers including Bahram Mobasher at UC Riverside contributed to the work. This map does not merely confirm the existence of dark matter, but it reveals its structure with unprecedented precision, tracing the cosmic web, the vast filamentary scaffolding along which galaxies form, at a level of detail that allows direct comparison with cosmological simulations. Early analysis suggests the observed distribution is broadly consistent with Lambda-CDM predictions, though detailed interpretation is ongoing. In December 2025, a study published in Nature Astronomy examined the shapes of young galaxies observed by Webb at less than 1 billion years after the Big Bang, and found them to be unexpectedly elongated. Simulations by Alvaro Pozo at the Donostia International Physics Center in Spain suggest that the observed elongation matches warm or wave dark matter models more closely than the standard cold dark matter framework. If confirmed by larger samples, this could provide one of the first observational constraints on the particle properties of dark matter, a question that has eluded physicists for decades. And in February 2026, a team of 48 astronomers across 14 countries, led by Jorge Zavala at the University of Massachusetts Amherst, published findings in the Astrophysical Journal Letters describing approximately 70 faint, dusty, metal-rich galaxies observed at roughly 1 billion years after the Big Bang. These galaxies, detected using a combination of the Atacama Large Millimeter Array and Webb, appear to represent a missing link in galaxy evolution, the transitional phase between the ultra-bright, actively star-forming young galaxies and the older, massive, quiescent galaxies like RU-BIES-EGS-QG-1. Their existence suggests that the shutdown of star formation in massive galaxies may have begun far earlier and far more gradually than the abrupt quenching assumed in most models. Each of these discoveries, taken individually, would constitute a significant advance. Together, they paint a picture of an early universe that is structurally complex, chemically mature, dynamically violent, and gravitationally organized on scales that models 3 years ago did not predict. The dark matter is where we expected it, but the galaxies embedded within it are doing things we did not expect, forming faster, merging more frequently, enriching their surroundings more thoroughly, and shutting down sooner than any simulation anticipated. And this brings us to the question that every viewer of this video, and every scientist working with this data, eventually confronts. the question that has generated more debate in astrophysics over the past 3 years than any other single issue. Does any of this break our understanding of the universe? The answer requires precision, because the question itself has been distorted in headlines, in social media, and in certain corners of the scientific fringe into something it is not. So, let us be exact about what is being debated, what is not, and where the genuine fault lines lie. The standard model of cosmology is called Lambda-CDM. Lambda refers to the cosmological constant, the term representing dark energy, the force driving the accelerating expansion of the universe. CDM stands for cold dark matter, the invisible mass that provides the gravitational scaffolding for all cosmic structure. Together, a Lambda-CDM describes a universe that began with the Big Bang approximately 13.8 billion years ago, expanded and cooled, formed the first atoms, and gradually assembled matter into galaxies, clusters, and the large-scale cosmic web we observe today. It is supported by decades of independent evidence: the cosmic microwave background, the distribution of galaxies, the abundances of light elements, the observed expansion history. It is not a guess. It is not a preliminary hypothesis. It is the most rigorously tested framework in the history of cosmology. And the critical point is this: nothing the James Webb Space Telescope has found contradicts Lambda-CDM at the cosmological level. The Big Bang happened. The universe is 13.8 billion years old. The cosmic microwave background is real. Dark matter and dark energy exist in the proportions measured by multiple independent experiments. These foundational pillars remain intact. What Webb has challenged is not the cosmology, it is the astrophysics within the cosmology. The detailed models of how galaxies form, how stars ignite, how black holes grow, and how quickly these processes can operate within the framework that Lambda-CDM provides. The distinction matters enormously, and collapsing it leads to confusion. Stephen Finkelstein at the University of Texas at Austin has been direct on this point. He stated that there is no crisis in terms of the standard model of cosmology. He added that any time you have a theory that has stood the test of time for so long, you have to have overwhelming evidence to really throw it out. And the evidence, while surprising, does not reach that threshold. Nashwan Sabti at Johns Hopkins and Julian Munoz at UT Austin published an analysis showing that existing Hubble ultraviolet data are inconsistent with modifications to the cosmological model, but consistent with astrophysical explanations, meaning the solution lies not in changing the rules of the universe, but in updating our understanding of how galaxies behave within those rules. Even after correcting for contamination by active galactic nuclei and errors in photometric redshift estimates, studies, including work by Kurofsky and colleagues in 2024, show that roughly twice as many massive early galaxies exist as models predicted. Twice as many is significant. But it is not catastrophic, and it can be accommodated by adjusting parameters within existing galaxy formation theory: higher star formation efficiency in primordial gas, bursty rather than continuous star formation episodes, and a top-heavy initial mass function, meaning the first generations of stars may have skewed toward more massive individuals, producing more light and more heavy elements per unit of gas consumed. These are not trivial adjustments. They represent a genuine rethinking of how the first galaxies operated, but they are adjustments within a framework, not the collapse of one. The cautious middle ground is occupied by scientists who acknowledge this, but refuse to foreclose other possibilities. Boylan Kolchin, whose own stress tests showed the severity of the tension, has stated that he does not think the case is airtight, that it has to be an astrophysical explanation. He has noted that what is propelling this crisis, potentially, is the fact that we are so data-rich now. The sheer volume and quality of Webb's observations have exposed uncertainties that were always present in galaxy formation theory but were previously hidden by the limits of our instruments. We are not necessarily seeing new physics. We may simply be seeing, for the first time, the full extent of our ignorance about old physics. And then there is the fringe. In the months following Webb's first images, a narrative emerged, amplified by certain media outlets and non-specialist commentators, that the James Webb Space Telescope had disproved the Big Bang. The most prominent advocate of this position was Eric Lerner, author of a book titled The Big Bang Never Happened, who claimed that Webb's images showed galaxies that were too smooth, too old, and too small for Big Bang cosmology. His argument gained traction online, drawing millions of views and widespread public confusion. The scientific community's response was unambiguous. Boylan-Kolchin stated explicitly, "Does this call the Big Bang into question? No. The Big Bang is extremely well tested." Alison Kirkpatrick at the University of Kansas, whose off-the-cuff remark about lying awake at 3 a.m. worrying about the data was taken out of context and used to support learners' claims, and changed her public profile name to Alison the Big Bang Happened Kirkpatrick. The episode served as a reminder that the gap between legitimate scientific debate and public misinterpretation can be vast, and that precision in language matters when communicating findings of this magnitude. There is, however, a separate and entirely legitimate cosmological tension that Webb has deepened. It is known as the Hubble tension, and it predates Webb by over a decade. The issue is this: measurements of the universe's expansion rate, the Hubble constant, derived from the cosmic microwave background, give a value of approximately 67 kilometers per second per megaparsec. Measurements derived from local observations, primarily Cepheid variable stars and Type 1a supernovae, give a value of approximately 73. The discrepancy is small in absolute terms, but statistically enormous, and no known source of systematic error has been able to explain it. The SH0ES team, led by Nobel laureate Adam Rees at Johns Hopkins, used Webb to observe over 1,000 Cepheid variable stars, eliminating crowding and blending effects that had been suggested as possible sources of error in Hubble's measurements. The result? The local expansion rate measurement held firm. Rees's team reported that measurement error could be rejected at 8 sigma confidence, a level of statistical certainty that, in physics, is considered definitive. The discrepancy is real. However, Wendy Friedman at the University of Chicago, using a different set of Webb-based measurements and distance calibrators, presented results in 2024 suggesting a Hubble constant of approximately 69 to 70 kilometers per second per megaparsec, potentially splitting the difference and easing the tension. The disagreement between Rees and Friedman, two of the most respected observational cosmologists alive, remains unresolved. It is possible that the Hubble tension reflects unknown systematic effects. It is possible that it reflects genuinely new physics, a modification to dark energy, an additional species of neutrino, or something not yet imagined. Webb has sharpened the question. It has not yet provided the answer. What we are left with, then, is a picture of extraordinary nuance. The James Webb Space Telescope has not broken our model of the universe, but it has broken our model of what the universe does in its first billion years. And the difference between those two statements is where the real science lives. Consider the full scope of what has been established over the course of this video. A telescope with a 6.5-meter mirror, orbiting 1.5 million kilometers from Earth, has observed a galaxy at a redshift of 14.44, 280 million years after the Big Bang. It has found galaxies with stellar masses rivaling the Milky Way at times when such galaxies should not exist. It has discovered supermassive black holes with mass ratios 30% or higher relative to their host galaxies, growing at rates that no standard model of accretion can comfortably explain. It has resolved the decades-old mystery of what reionized the universe, revealing that the smallest galaxies, not the largest, did the heavy lifting. It has detected oxygen at a redshift beyond 14, proving that stars had already lived and died when the universe was barely 2% of its current age. It has found spiral galaxies with fully formed structure billions of years before such structures were supposed to emerge, and it has mapped the distribution of dark matter with double the resolution of any previous instrument, confirming the cosmic web while simultaneously revealing that the galaxies within it are behaving in ways we did not anticipate. None of these findings existed 4 years ago. Every single one emerged from a telescope that has not yet completed its 4th year of operations, with an estimated 17 years of fuel remaining and scientific demand at an all-time high. Rohan Naidu, the lead scientist behind the most distant galaxy ever confirmed, wrote that previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away. He is not being poetic. He is being precise. The boundary of the observable universe, The point beyond which no telescope, no matter how powerful, can see is not a wall. It is a horizon that moves with each improvement in sensitivity and wavelength coverage. And Webb is approaching it at a pace that has surprised even its architects. The models will be revised. They are already being revised. Star formation efficiency in the early universe will be adjusted upward. The initial mass function may be recalibrated. Black hole seeding mechanisms will be refined, tested, and likely expanded to include pathways that were considered exotic 5 years ago. The astrophysics will adapt, as it always does when confronted with better data. That is not a weakness of science, it is the mechanism by which science works. But there is a deeper lesson in what Webb has shown us, one that extends beyond the technical details of redshifts and stellar masses. For decades, our picture of the early universe was defined as much by what we could not see as by what we could. We filled the darkness with assumptions, reasonable, well-motivated assumptions built on the best available data. And those assumptions told us that the first few 100 million years were a quiet, tentative time, a slow ignition, a gradual awakening. Webb has shown us that the universe did not awaken gradually. It erupted. Stars formed in quantities and at rates that defy our models. Black holes grew with an urgency that our physics struggles to accommodate. Galaxies assembled structures in hundreds of millions of years that we thought required billions. And the smallest, faintest objects, invisible to every previous generation of telescopes, reshaped the chemistry of all space. The universe, it turns out, did not wait for permission from our theories to begin. And yet, what Webb has revealed so far may represent only the outermost edge of what is coming. Because there is a region of cosmic history that remains almost entirely unobserved, the period between the release of the cosmic microwave background, 380,000 years after the Big Bang, and the formation of the first luminous objects. The true Dark Ages. And a span of perhaps 100 to 200 million years during which no photons were emitted by any source other than the cooling afterglow of the Big Bang itself. Webb cannot see into that epoch directly. No electromagnetic telescope can. But it is pressing closer to its boundary with every observation cycle. When JADES-GS-Z14-0 was confirmed at a redshift of 14.32, the scientific community absorbed it and moved on to the next observation. When MOM-ZER14 arrived at 14.44, just 10 million years closer to the Big Bang, it was not merely a new record, it was a signal. The gap between what we can observe and what we cannot is narrowing, and the objects being found at these extreme distances are not fading into obscurity as they approach the boundary. They are bright. They are chemically complex. That they are doing things. This means one of two things. Either the very first stars and galaxies formed in a sudden coordinated burst, a near simultaneous ignition across vast regions of space, or there are objects at even higher redshifts, even closer to the Big Bang, that Webb has not yet detected. Objects that formed the heavy elements found in MOM-Z14, objects that produced the radiation that was already clearing the neutral hydrogen around it. Predecessors. And if those predecessors exist, they are waiting in the data that Webb is collecting right now, in the Cycle 4 observations currently underway, and in the Cycle 5 programs that begin in July 2026. The 254 programs selected for Cycle 5 were drawn from nearly 3,000 proposals. Among them, the multiple programs are specifically designed to push deeper into the first 300 million years, targeting gravitationally lensed fields where the magnification of foreground galaxy clusters acts as a natural telescope, amplifying the light of the most distant objects to detectable levels. Other programs are hunting directly for the spectral signatures of population 3 stars, the theorized first generation formed from pure hydrogen and helium, never yet confirmed. If those stars are found, when those stars are found, it will represent the detection of the first light that ever shone in this universe. Not metaphorically, literally. The scale of what is at stake is difficult to communicate because the numbers involved exceed human intuition, but consider this framing. The observable universe contains an estimated 2 trillion galaxies. The light from the most distant of them has traveled for over 13.5 billion years. The galaxy we now call MOM-Z14 is, due to the expansion of space, currently 34 billion light-years away from us. We observed it as it was when the entire observable universe, everything we have ever seen or will ever see, was compressed into a volume less than 1/50th its current size. The stars within it had already formed, already fused hydrogen into helium and helium into carbon, and carbon into nitrogen, already exploded, and already seeded their environment with the raw materials for the next generation of stars. All of this in 280 million years. The Earth is 4.5 billion years old. Human civilization, generously defined, spans perhaps 10,000 years. The light from M-C14 began its journey toward us over 13 billion years before our planet existed. And when it finally arrived, captured by 18 gold-plated mirrors orbiting a point in space 1.5 million kilometers from a small rocky world in an unremarkable spiral galaxy, it told us something we did not expect. It told us the universe was already busy, already working, already building. There is a sentence that appears near the end of Jacob Shen's commentary on the MOM-Z14 findings. He wrote that there is a growing chasm between theory and observation related to the early universe. It is a careful sentence, measured, precise. The kind of sentence a scientist writes when the data is clear but the explanation is not. A chasm is not a contradiction, and it is a gap, a space where understanding has not yet arrived, but where the ground on both sides is solid enough to know that something must eventually bridge it. That is where we stand. On one side, a cosmological model that has survived every test thrown at it for a quarter century. On the other, a telescope delivering observations that the model's astrophysical predictions did not foresee. The bridge between them has not yet been built. It may require revised star formation physics. It may require new black hole seeding mechanisms. It may, ultimately, require modifications to our understanding of the very early universe, the behavior of dark matter, the nature of the first gravitational collapses, the physics of gas cooling in a universe with zero metallicity. Whatever the answer turns out to be, it will not come from theory alone, yet it will come from data, and the James Webb Space Telescope is producing more of it, at higher quality, across a wider range of cosmic epochs than any instrument in the history of science. It has been operational for less than 4 years. It has enough fuel for approximately 17 more. And the questions it has raised in its first 4 years are, by the consensus of the scientific community, among the most important in modern astrophysics. Bring this back to where we began. A galaxy at redshift 14.44, 280 million years after the Big Bang, observed, measured, confirmed, containing stars that had already lived and died, surrounded by gas already enriched with heavy elements, already clearing the primordial fog of neutral hydrogen. And it looks nothing like what we predicted, not because our predictions were careless, but because the universe, in its infancy, was more capable than we imagined. Every generation of telescopes has pushed the boundary of the observable universe outward, and every time, what was found at the new frontier was stranger than what came before. Hubble showed us that galaxies existed at redshifts beyond 10. Webb has shown us that at redshifts beyond 14, galaxies were not only present, they were thriving. They were enriched. They were structured. They were, by any measure, more advanced than they had any right to be. And somewhere beyond them, beyond the current reach of even Webb, the very first stars that ever existed are waiting to be found. The first photons of starlight that ever traveled through this universe are still out there, stretched to wavelengths we can barely detect, carrying information about a moment no human has ever witnessed. The moment the Dark Ages ended, the moment the universe stopped being empty and started becoming everything we see around us. The James Webb Space Telescope was built to find that moment. It has not found it yet, but it is closer than anyone expected to be this soon, and every observation it makes, every cycle it completes, every record it breaks, brings that boundary a little nearer. The edge of the observable universe is not a place. It is a question. And for the first time in the history of our species, we have an instrument capable of answering it.